once you get to the, let's call that one,
Oh yeah, it's just
right?
meta
It's going to be
director.
meta anyways. To, right?
Yeah.
And then you're reducing the acyl to alkyl. So there was no need for the blocking part in this. Everybody agrees with that? So you're talking about activating effect, deactivating effect, and directing effect to kind of sequence your steps. So if we do the same here, I think we should safely take that away. You don't need to block any positions, which means you don't have to unblock a position either. So now you're acylating first, putting an acyl group, reducing it, and then brominating, because when we, but here's a problem though. Here we will have a problem in this case. So here's what you are doing. Please tell me what would be the problem. So not just you, everybody. So step number one, if we acylated, did you use Cl? Yeah. We'll get an acyl group on benzene, and then you're reducing it, you're doing Clemenson, so you're reducing it, so acyl becomes alkyl. Agreed? Everybody okay? Mm-hmm. Now, I want bromine in the ortho position. If I did bromination, what will be the major product?
Para,
Why?
because the methyl's bulky.
You mean propyl?
The propyl's bulky.
It's going to block the ortho positions.
Mm-hmm.
So here we probably, that would not be the major product. So here we do have to get a little creative. So here you probably definitely, not probably definitely, here you definitely, fusing, what is fusing?
Fuming?
Fuming H2SO4, or H2SO4 plus SO3, yeah, absolutely. Because we want to block this position so that the electrophile doesn't go here, it goes there.
Mm-hmm.
So now we need a blocking group. We definitely need a blocking group here to push the bromine. Where would that push the bromine now?
Ortho position.
And therefore, we now need to unblock. Does that make sense, everybody? So here we do, yes, because you don't want, otherwise the major product will put bromine in the para position and not the ortho, but we want all of it. Does that make sense, everybody?
Yep.
Mm-hmm.
Cool.
I'm sorry.
Yes, please.
Just real quick.
Yes.
For that one up there that's the direction, and for the
Second.
one, wait.
Where, what?
Yeah.
Which part?
No, I'm just wondering.
Yeah.
I'm sorry. I was a little bit spaced out. And this is for this.
Yeah.
This is the correct one.
Yeah.
And this is
For
this,
that second one,
which
yeah.
starts
Right here. Starts here, from here to there. Yeah,
Thank you.
yeah, yeah. So, sorry, I'm messing, yes. This one. Is that okay, everybody? Okay, next one. So we need metachloroaniline. So you nitrated it first. Okay, so that won't work.
Yeah.
What very quick change can you make and then it'll work? Actually, you're missing a step too, but we'll get to that part.
Some NaOE.
So what I'm assuming, yeah, you're missing a step, you're right, we'll get to that part in a second. But what you're trying to do, I think this is what you're trying to do. You nitrated it, right?
Yeah.
And what is the purpose of step 2?
Turn it into NH2.
So, as soon as you turned it into the nitro into NH2, is this ortho-para director or meta director?
Ortho para
Ortho,
directed.
sorry.
You won't get the meta. That's the point, right? Does that make sense?
Yes, yes.
So, what quick change can you make? And then it'll be fine.
To not add it into
Fuming
our-
sulfuric.
Oh, that's
acid.
what it's okay. I forgot that it be added.
Nitro is meta director. Have nitro, then put the chlorine which goes in the meta position, then reduce your nitro to aniline, but Carter is also right. So this becomes step 2, this becomes step 3, but remember you need a step 4 with the reduction. If you have HCl, you got to neutralize the HCl. Otherwise you won't have aniline, you'll have the salt of aniline.
Okay.
Yep, so just switch that order. So here you put chlorine first and then did the reduction once again. If you're going to reduce the nitro to amine and there's an acid there, amine is a base, you won't get the amine, you must basify it.
Okay.
But that's okay, that's fine because halogens are also para directors, so that's totally fine. Okay, what did we do here? So there is no, this, I don't know who did this, I'm not going to look at anybody, but no, let's not do that. You can't just put a chlorine anywhere and have it do Friedel-Crafts alkylation or acylation. Acylation uses an acid halide. That's not an acid halide, I don't even know what that is actually, to be honest. Acid halide is with an R. We can't just put anything we want to, just because that's what it looks like. So you got to be a bit creative about it. So no, that one probably not probably, that one definitely not. So also, even if it were something, the regiochemistry won't work out because that is going to be a meta director, but we want nitro in the para position. So you got to think about that. Any suggestions? Suggestions?
Chloro, without the same ClO, but without the proton.
Proton, what do you mean proton? Where's the,
Oh.
so are you saying ClOO? I mean this?
Yeah,
What is
Cl.
that?
No.
What is
How about
that?
just without the O? No.
What is without the, what is that?
No.
Oh,
I was trying to say methyl. Methyl.
oh, you want to put a CH3 there?
Mm-hmm.
That?
Yeah.
Okay, so this one we can work, so what you're saying is use an acetyl chloride basically
Mhm.
with an, is that what you're saying?
Yeah. Mhm.
Okay, so if you do that step with AlCl3 in step number 1, what will be the outcome? What will that produce? Which reaction is this?
The backwards,
Friedel-Crafts
like
acylation.
Friedel-Crafts
ketone, yeah.
acylation.
Mhm.
Okay, cool.
Friedel-Crafts.
You got Friedel-Crafts acylation, you'll get a ketone.
Mm-hmm.
What will you do next?
Mm.
And remember, we want
And
para.
nitrated?
You can't
No.
because that's meta director.
Oh. So how about nitrated first?
That's a meta director too. And in fact,
Fuming sulfuric acid
to do what?
as a blocking group.
Okay, which group will it block? Meta positions. Isn't that right? You basically what you're thinking is, okay, we could, tell me, and remember we're all brainstorming here. We're just brainstorming, we're just throwing ideas to see where that takes us. That's kind of the process. Okay, so, oh, sorry, I did that wrong. I'm so sorry. It's a meta, so meta. Or this.
Or there.
One
Yeah, I
of
was
these.
wondering.
Yeah, no, they're both.
Yeah.
You can draw that. Agreed?
Agree.
Okay, then do what?
Can you do? Oh, sorry.
Nitrated.
Okay, where will it go? It'll go to the meta position. They
It'll
are
go to
both
the other
meta
meta
directors.
position.
Yeah.
We still won't get what we want
Can
though.
you do Clemenson's
Louder please.
reduction?
Okay, so what you're saying is once you acylate it, reduce it into an alkyl group. Is that what you're saying?
Because then it will become a,
I need more space. Okay, so Clemenson or Wolff-Kishner or whichever, basically use something to convert it into an alkyl. Is that what you're saying?
That's what I'm saying.
Okay, because now it is an orthopara director. Isn't that right? Now that's an orthopara director. Okay, so now if we did, so what's the next step?
So then if you do nitration, then it will probably go para because ortho's sort of blocked. I would have used a longer alkyl group?
I would, exactly, because to make it, if that's a choice, if you don't have a choice, that's a different story then. But if you have a choice, let's make it longer so that makes sure that your para position is the preferred position.
Right, because then you can just do the chromic acid and into your carboxyl
Sorry,
group.
excuse me.
Oh, it's after
excuse
you
me.
nitrate.
After we nitrated, and then how do I get the carboxylic acid?
Chromic acid.
Exactly. Remember the oxidation of the side chain. Oxidation of the R side chain converts no matter what the size of the R group is into carboxylic acid. And you can either use the chromic acid version or this potassium permanganate version, whichever. The R group on the benzene can be oxidized no matter what the R is, except there's one of the R's that
Tert-butyl.
exactly. So no matter what the R is, except T-butyl will become a carboxylic acid. So that is the way to get benzoic acid. Everybody okay? So the point that we are establishing here is it's all about sequencing things. It's all about putting things in the order that makes sense to get the right regioselectivity and chemoselectivity. Questions? So these are these are electrophilic aromatic substitution reactions where a hydrogen on the benzene is being substituted by an electrophile. The 5 main categories of electrophilic aromatic substitution reactions are halogenation, nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation. You must know the mechanisms for all of these. So, excuse me. But it is also possible to perform nucleophilic aromatic substitution reactions. So let's look at this. Do you guys remember SN2, SN aromation? What is going on? Do you guys remember SN1, SN2 reactions?
Yes.
SN2 targets a primary.
Okay,
And
do you guys
secondary.
remember?
Yeah.
What kind of carbon atoms do SN1 and SN2 happen on?
SN2.
SN1 and SN2 always happen on what kind of carbons? sp3 hybridized.
sp3 hybridized carbons.
Are the benzene carbons sp3, sp2, or sp?
sp2.
So, can benzene, carbons of the benzene, can they go through SN1 or SN2? No. Yet it's going through a nucleophilic substitution, but not SN1 or SN2. This is called SN substitution nucleophilic AR, aromatic. Completely different mechanism, completely. Because SN1, SN2 is specifically for sp3 hybridized substrates. So again, the idea is if there is a leaving group and if we have a nucleophile, then the nucleophile can substitute the leaving group and give us the new product. But it cannot be SN1 or SN2. It's a totally different mechanism. Now the mechanism for SNAR can be one of 2 different kinds actually. It depends upon the aromatic substance.
Was that AR or AR?
AR,
Oh.
aromatic, AR, yes. Okay, so it can be of one of 2 different kinds. The first kind is benzene with strong electron withdrawing group on it. So if you have a benzene that's extremely electron poor, Also, actually, maybe important to note electron withdrawing on ortho or para to the leaving group, specifically speaking. Specifically there because again by resonance that creates a more stable intermediate and transition state. So for example, if we have, let's say, a leaving group, same leaving groups as before. The leaving groups are exactly the same as what you've seen before. So can that be a leaving group? We've seen it before.
Yes.
But with a strong electron withdrawing group, ortho or para, either in the ortho position or the para position, to the leaving group. And then if we react this with a nucleophile such as hydroxide, can someone tell me what will be the expected product? And then we'll write the mechanism. Anyone?
Swap the Cl for OH.
Sorry, could you say that one more time?
Swap the Cl for OH.
So phenol you mean?
Uh-huh.
Orthonitrophenol? That's exactly what you meant, right?
That's exactly.
Perfect. Substitute. Now please note guys, you know all the reactions that we've seen so far in this chapter, the electrophilic aromatic substitution reactions that we've seen in this chapter so far, what was being substituted by the electrophile?
A hydrogen.
Right? Everybody notice that? Here it's not the hydrogen that's being substituted by the nucleophile, not electrophile. A, we have a nucleophile, not electrophile. And B, it's a leaving group that's being replaced, not the hydrogens.
Is it what?
Hydrogens are not being replaced, it's the leaving group that's being substituted. You guys notice that? So please notice these differences. I'll summarize everything a little bit later. So let's see what the mechanism looks like. Is it going to be SN1? Is the mechanism going to be SN1?
Well, SNAR?
How about SN2? It has to be SNAR. It's a totally different mechanism. I'm driving home at the fact because I don't want anybody to draw me a carbocation or make a transition state because no, that's wrong.
SNAR.
This is a different mechanism as one of those SNARs. SNARs are of two different kinds, but yes, you're absolutely right. So let's see what that looks like. We have a leaving group and we have the electron withdrawing group ortho to the leaving group. Step number 1, the nucleophile attacks the carbon with the leaving group, but it is not SN1, it is not SN2. So the pi electrons shift. Sorry for that curve thing because I didn't have enough space there.
It's pretty cool, actually.
The point is that the pi electrons go there. Can you draw for me what that will create? Please draw for me the intermediate. This is an intermediate, it's not a transition state. This is actually created. Do you guys agree?
Yes.
What am I missing?
The charge?
Hydrogen, I didn't take away any hydrogens. I mean, there's a hydrogen.
The charge?
Where, what? Where and what?
Carbon.
It should be a negative
Where?
in the middle.
A carbon.
Now do you understand why the electron withdrawing groups is so important here? The electron withdrawing group is so important here because this negative charge, what do you think the electron withdrawing group can do to the negative charge?
It'll suck the electrons in.
And will that stabilize or destabilize the intermediate? Exactly.
Stabilize.
Exactly. So that is why we need a strong electron withdrawing strategically in either the ortho positions or the para. I'll give you an example with para also in a second. But because we end up with a negative charge, and that negative charge, of course, there's resonance over there in the ring, but there is also, the group also takes that electron, the electron density away, stabilizes the anion. Everybody okay? And then comes the next step. What does this have to do to become the product? Exactly. Makes the double bond again, it's aromatic again, kicks out the leaving group. What does that produce? It produces the product,
The phenol product.
and the leaving group is kicked out. Cl minus kicked out. But do you see what's going on? It's actually kind of sort of like addition followed by elimination. Two steps kind of thing where we are adding, creating a carbon ion that is stabilized by resonance and the electron withdrawing group, and then elimination, recreating the pi bond, kicking out the leaving. Does everybody see that? Yes? Okay. Please understand this mechanism is only when there is a strong electron withdrawing group in the ortho or the para position to the leaving group. So let's try it one more time. If I have and I am reacting this with what will be the product?
OCH3 instead of BR.
Instead of,
BR.
right? Do you all agree? Anisole, basically an anisole product. So the leaving group is Br, as we've seen it be a leaving group many times. It's being replaced by the methoxy group, so we get anisole, trifluoromethyl anisole. Para trifluoromethyl anisole. Let's write a mechanism. Let's try and understand how this is going to happen. So once again, please notice, these are the things we got to focus on. Is it a nucleophilic substitution or electrophilic substitution? A.
Nucleophilic?
Because a nucleophile is coming in and hydrogens are not being substituted,
Yes.
right? B. Is there a strongly electron withdrawing group in the orthopara position relative to the leaving group?
Yes.
Very, right? So then this mechanism works. So let's write it. Let's see what that is going to look like. First step, anybody?
The methoxy
Attacks the what? Of
attacks
the
carbon with the bromide on it.
And what about the pi electrons? Agreed? Let's see what that creates. Where's the minus? Right.
Yep.
Agreed?
Mm-hmm.
Now, how does CF3 in the para position help stabilize the negative charge?
Resonance?
Exactly. It's an allylic carbon ion. If it's allylic carbon ion, can there be resonance? Can there be resonance there? Absolutely. Absolutely. But we didn't need to think about it because the leaving group was right there so we could see it. But can there be resonance here?
Yes.
Let's draw it out. I'm just going to draw it on the side so we can see. Let's draw it out. One of them at least. Of course, more than one is possible. Do you agree that one of them... If I take those electrons, push them here, push it here. Yes? Now once again, notice where's the negative charge sitting.
On the carbon attached to the electron.
So the leaving group, if there is a strongly electron withdrawing group either in the ortho position or the para position, or both, to the leaving group, then this mechanism happens. Anyways, coming back, what's the next step? Once we get the intermediate, what's the next step? The next step.
The anion forms a double bond. The electron
Exactly,
goes
and-
out the double bond.
kicks out the,
Takes
you
out
get
the
the
leading
product.
group.
Exactly, and you get the product. So this mechanism is one of the possible SNAR mechanisms, which is specifically when there's a strong electron withdrawing group next to the ortho-para to the leaving groups. Then we can do this. Everybody okay? Cool? Okay. But SNAR can also happen without a strongly electron withdrawing group ortho-para to the leaving group, which has a different mechanism. So, can we do a nucleophilic? Again, keep in mind this is nucleophilic aromatic substitution without the answer is yes, but we need way stronger conditions. We need the conditions to be extremely, extremely strong. And this reaction can happen, so basically it will need a lot of heat. We might have to fuse the nucleophile and, basically the point is we need strong conditions. And this reaction again is best if you have strong nucleophiles. So namely, if you have these be nucleophiles, then the reaction is better. But the mechanism cannot be that because there is no electron withdrawing group anywhere in this ring, right? Now, so this, by the way, when you looked at this mechanism, there was addition happening first, followed by elimination, right?
Mhm.
This one is opposite. Elimination first, addition after. So let's look at it. You're probably going to see an intermediate in this reaction, which seems to be very strange. It's like, wow, what? But yes, it exists. So let's talk about it. A good nucleophile is also, a strong nucleophile is also a strong,
Base.
right? So here, the nucleophile, instead of acting as a nucleophile, actually acts as a base first. What does the base do? Let's say hydroxide in this case. What does the base do? Takes a proton. Where will it take a proton from? It will take a proton from the ortho to the leaving group. Takes a proton ortho to the leaving group. But if it's going to take the proton, what's going to happen to those electrons? Well, if that happens, what happens there?
Leading group. is kicked out.
Elimination reaction. This is elimination. We've eliminated HCl if you think about it. Isn't that right? Can you draw for me what would this create? You will see this intermediate only in this reaction.
Hmm.
An alkyne and a benzene.
Can it bend like that? Why?
It's very unstable. It's highly unstable. You're absolutely right. I'm glad you're looking at that. Look at those hybridizations, SP hybridize and SP2
Yeah.
hybridize. Can it really? That's a great question. And
usually
the
a straight
answer
line.
is, yeah. How do we know? Because we've tracked it. We not like I wasn't invited to that party. Point is, there's research about it. Where
Humans.
this has been tracked. How, by the way, here's the interesting part. Do you know which reaction was used to trap this? Diels-Alder reaction
Diels-Alder.
that we learned last quarter. Basically, they did the again, there's research about it, and they trapped this in with a diene, dienophile. This acted as the diene and then looked at, analyzed that product and said, whoa, that's the only way we can have this. So the point is, long story short, this exists. Funny thing, it's an alkyne of benzene. What would you call it?
Benzine.
Absolutely. It's not, it's a very unstable. Please, don't, I'm not in any way trying to say this can be stored in a bottle. Not at all. It's highly unstable, highly unstable.
So,
But it does exist as an intermediate.
quick.
Yes, exactly. So, once benzene is created, because it's unstable, it wants to get out of it. What does it do after elimination? It does addition. What is going to add across that new pi bond?
An OH.
Not just an OH. Adding, you add two things, right? Whenever we do addition reaction, a part goes here, another
Like
part goes
the
there.
water?
Water. Because we created water right here. Created water right there. So water adds across the pi bond. When water adds across the pi bond, it can either add that way or it can add this way. Absolutely. It can either, water molecule can either go this way or it could go that way. Of course, in this case, it doesn't matter whichever way it comes, but what's the result?
Phenol.
This is also substitution nucleophilic aromatic benzene mechanism, some people call it. Now please understand this mechanism we should think about when there is no electron withdrawing group on the benzene ring. Please notice there is no electron withdrawing group on the benzenes as we are doing a nucleophilic substitution. That's when we think of this mechanism. Does that make sense, everybody? Do you see the differences between the two mechanisms? That one is addition first, followed by elimination. This is elimination first, followed by addition.
These two are the same, right?
Yes, those two are the same.
Addition.
Everybody okay? Let's try the benzene mechanism one more time, just to get the feel for it, so to speak.
So that's called benzene mechanism.
Yeah, because there's benzene in there as the intermediate, so benzene mechanism. Okay.
But if we see just the two up there, we won't know until we do the mechanism, right?
What do
Or
you
how
mean?
do we know?
Yes,
That
exactly.
it's
How
seven-
do you know?
Uh-huh.
We just said, should have an electron withdrawing, strong electron withdrawing group, ortho and para, ortho or para with
Oh.
respect to the leaving group. Then you gotta do this. There is no electron withdrawing group, ortho or para.
Oh, mhm.
That's how you know.
Okay.
Okay, please, try this. So here's an example. This can produce two products in about equal quantities. There's really no selectivity. Question is, what are those two products, and write a mechanism. Think about this. Two products, and I'm talking about organic, I'm not talking about byproducts, I'm talking about the organic products. So two organic products, what are they, and mechanism. So first of all, is there a electron withdrawing group close to or ortho or para to the leaving group? Yes, no, maybe.
There's an electron
There's an,
donating.
okay, but that's not the question I asked, right, Carter? Is there an electron withdrawing group ortho or para to the leaving group?
No.
No. So, if that's the case, which aromatic substitution mechanism will it do? Will it do the one that does addition and then elimination, like we saw earlier? Or will it do the benzene mechanism?
Addition elimination.
But there is no electron
Electron.
withdrawing
So we
group,
have to do benzene.
ortho or para, please. That,
Benzene.
right? That mechanism that we did before, the addition elimination one, is specifically when there is a strong electron withdrawing group either in the ortho position or the para position to the leaving group. If that is not the structure, then it's the benzyme mechanism. We good, everybody?
Mhm.
Okay. So with that in mind, can you tell me what are the two possible products we will get, and we will of course write mechanism. Yes.
Oh,
I'm
I thought you were asking for
thinking,
the product.
Yeah, please do.
Oh, write it up there?
Yeah, why
I don't know
not?
the mechanism yet, I just know what the.
Write what you know. That's fine. Please. Oh, what happened? I thought you were. Okay. Carter beat you to it.
Well, there's two products, right?
Oh, you. Okay, let's see what Carter writes then. Then we see. Okay, Carter wrote one. So what's the other? No, give it your best shot. That's okay. Just try it.
yes, do it.
What did you have in mind? I think you had it in your mind. Now you're questioning yourself. Your gut told you exactly what it was supposed to be, and then let your brain come in the way.
That's what I think, yeah,
Okay.
but I don't know.
Perfect. Exactly. Exactly.
Meta.
We'll either get orthomethyl aniline or meta-methyl aniline. How? Let's try and explain this based upon.
I see now.
You see it? Where, can you see my pens too, Vincent? Where did I? Oh, there we go. Sorry. Yes, I think you see it, right? Because when you're doing the second step, the addition step, the thing, whatever it is you're adding, can either come in this way or it can come in this way. Exactly. So this is benzyme mechanism. Absolutely, it's benzyme mechanism, which means that the base, not nucleophile, the base, because they are pretty strong bases, are going to come and take a proton from which position? Which position does it take a proton from?
The ortho?
Ortho to the leaving group. Is there a hydrogen here?
Yes.
Yeah.
No,
Careful
no, no,
now.
no, 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 no.
No, no proton.
Carbon with four
No, no.
bonds.
Nope.
Is there a hydrogen there?
Yes.
So in this case, there's only one option, right? Takes the proton, creates a benzyme, kicks out the leaving group. So if it creates a benzyme intermediate, do you agree? And now the addition happens. What is adding?
NH2.
NH3.
NH3. There's H, NH2, which ammonia, you created ammonia. NH3 is adding. So once again, NH3 could either come in this way, or NH3 could, oops, that's the same, or it could come in this way. Make sense, everybody? Yes?
So the mechanism's the same up until that point, right?
Mechanism is the same the other way too, exactly.
Mhm.
The only thing is the direction of the approach. It either comes in this way or comes in this way, which means that we will either get NH2 attached here and H attached there, right? H went here, NH2 went there. And, not or, and, because you will get both products in equal quantities. There is no selectivity for one or the other. or NH2 will go here, H will go there. So two products. Does that make sense, everybody?
Yes.
Everybody okay? Sounds good? Yes? Okay, if that makes sense, please tell me. How many products and what are they? How many products and draw the products? Anybody? How many products?
3 products.
3 products is what I'm hearing. Do you guys agree? What 3 products?
One in the parameter and ortho.
So you mean paramethyl-aniline, metamethyl-aniline, and
Ortho.
orthomethyl-aniline? Is that what you're saying? Everybody agrees? Is that a yes?
Yes.
Yeah.
Why 3 products? Can you write a mechanism to show how we get these 3 products? Thank you. So this is benzyne mechanism. And this mechanism is a nucleophilic aromatic substitution reaction without a strong electron withdrawing group on the benzene ring. This is the only time you will see benzyne. Yeah. That's a good question. I would still not go benzyne because it's such a strange system. Okay, if it's a strong electron withdrawing group like nitro, CF3, because those are strong electron, I would not do benzyne. I would do the other one. It won't obviously be as fast as if they were orthopara, but still there is a lot of stabilization of that intermediate by the electron withdrawing group. I would leave the benzyne for when there is no electron withdrawing group at all on the benzene ring. Yeah.